Just take a look at this. I mean, this is not science fiction. This is the actual heat shield for the Orion spacecraft, a truly monumental piece of engineering that's designed to keep astronauts safe when they come blazing back from the moon. And it's built from advanced composites, materials that are literally shaping the future of high-stakes tech.
But, to create something this advanced, you need some seriously advanced manufacturing to back it up. It all starts right here, inside these gigantic, high-pressure ovens called autoclaves. This is where the raw materials get cooked into parts that are both incredibly strong and unbelievably light.
And that really brings us to the core question, right? When you're building for space, or for massive renewable energy projects, or for national defense, there is absolutely zero room for error. Failure is just not an option. So how on earth do you make perfect parts every single time?
Well, this is what we call the composites conundrum. On one hand, you've got this incredible, almost magical wonder material. But on the other hand, actually producing it perfectly is one of the single biggest challenges in modern engineering today.
So why even bother with all the hassle? Well, because composites are a total game changer. They're way lighter and stronger than metal, which is exactly why they are absolutely essential for everything from satellites and launch structures, yeah, think SpaceX, all the way to those enormous blades on wind turbines.
For decades, the undisputed gold standard for making these parts has been the autoclave. The best way to think of it is as a giant industrial-strength pressure cooker. You've got intense heat and massive pressure that consolidates the material, squeezing out any imperfections to get maximum strength. It works, and it works really well. But it's also incredibly expensive, it's slow, and you just can't use it to build things on a truly massive scale.
The reason the whole process is so intense is because manufacturers are fighting a hidden enemy, defects. We're talking about tiny, almost invisible flaws that can pop up during production. And even the smallest one, well, it can lead to catastrophic failure down the line.
It pretty much all comes down to this one number, less than 2%. For any part that's going into an airplane or a spacecraft, the total volume of tiny air bubbles, what engineers call voids, cannot be more than that. The margin for error is, well, it's practically non-existent.
And this image shows you exactly what we're talking about. On the left, a part that's just riddled with those voids. See all those dark, empty pockets? That's a failure, total scrap. But on the right, that's the goal. A dense, solid, high-quality part. A perfect structure that you can trust.
And it's not just about the voids. Engineers are fighting a whole host of these potential defects. You've got parts warping out of shape, fibers getting knocked out of alignment, dry spots where the resin didn't quite flow, and even tiny micro cracks you can't even see. It is a constant battle for perfection.
So these limitations, the cost, the size, they forced the industry to innovate. There just had to be a way to make parts that were cheaper, bigger, and faster, all without giving up an inch on quality.
And that's where Out of Autoclave, or OOA, comes in, along with another process called VARTM. Now, instead of a massive high-pressure oven, these processes use vacuum bags to literally suck the resin through all the fibers. This is a revolutionary idea because it's way cheaper and it lets you build enormous structures, like an entire airplane wing or a giant turbine blade, all in one single piece.
Okay, and this is where it gets really interesting. This is the critical trade-off. Autoclaves get their control through sheer brute force, just tons of pressure. But these new OOA processes, they don't have that crushing pressure to rely on. So to keep those defects out, they demand an unbelievable level of precision and control over every single second of the process.
And yeah, here's the catch. As this source points out, by ditching the autoclave, you're really just trading one huge challenge for another. These new, more flexible methods are much harder to control. Suddenly, that fight against hidden defects just got way more difficult. So how do you get that kind of precision?
The answer, amazingly, comes from a completely different world, the digital world. To truly master these new physical processes, manufacturing needed a digital revolution. It needed a brand new toolkit, one powered by data, sensors, and artificial intelligence.
So the first tool in this new kit is something called dielectric analysis, or DEA. Basically, these are tiny sensors that you put directly inside the composite material. As the material cures, its electrical properties change, and these sensors measure that change in real time. It's like giving engineers eyes inside the part while it's being made. It's incredible.
And this is what those sensors are seeing. This graph shows you exactly how the material is behaving. See that blue curve?
That's called ion viscosity, and it's basically the fingerprint of the cure process. Engineers can watch it, track it against a perfect golden curve, and know the exact moment to tweak the temperature or apply pressure to get a flawless part.
What's next? Automated inspection. This used to be insanely expensive, but today, thanks to huge leaps in computer vision, you can use simple, low-cost cameras hooked up to a cloud-based AI to scan for defects as the part is being built. It gives you instant feedback, catching flaws the second they appear.
But AI can do so much more than just find flaws. It can actually prevent them from happening in the first place. With machine learning, you can just feed an AI all your design rules and what you need the part to do, and it can generate the perfect design for both strength and for easy manufacturing. It's essentially taking all the knowledge of expert engineers and digitizing it so anyone can use it.
And all of this, it all comes together in this incredible concept called the digital twin. This is the ultimate tool. It's a living, breathing, virtual copy of the entire manufacturing process, from the raw materials all the way to the finished product. It pulls in data from those DA sensors, from the vision systems, from every machine on the factory floor, and puts it all in one place.
So what can you do with a virtual factory? Well, you can run an entire production simulation and predict the quality of a part before you even start making it. It can spot risks, like a machine that's about to overheat or a bad batch of material, and flag them before they turn into expensive mistakes. It completely flips manufacturing from being reactive to being proactive, a smart system that actually anticipates problems.
What we're really watching here is the birth of a truly intelligent future for manufacturing. It's not just about coming up with better materials anymore. It's about inventing a fundamentally better, smarter way to build things.
When you think about it, this whole journey was driven by necessity. The incredible challenge of making perfect composites pushed the industry to invent new processes like OAA. And then, mastering those processes demanded a complete digital transformation, a fusion of the physical world of manufacturing with the world of data and intelligence.
And maybe the most powerful result of all of this is this right here. The same tech that makes it possible to build things like spacecraft heat shields is also making advanced manufacturing accessible to everyone. These low-cost AI design tools mean that small and medium-sized businesses can now innovate in ways that used to be possible only for the giant corporations. It's the democratization of high-tech manufacturing.
Which really leaves us with one final big question. We've seen how this revolution is totally reshaping aerospace and energy. But what happens when anyone, anywhere, can design and build with these amazing materials and intelligent systems? What other monumental challenges could we solve then?